All right, guys, with that last assessment, you just finished your fourth and final standard of the NS strand. What does NS stand for? Number system. Now, it's called number system. Do you think we're ever actually done with it in class? No, never. It's always going to come back like all things mathematics do. But you had 4 official standards in the number system strand. You learned, you took everything you did with adding and subtracting through elementary and rational numbers. And those were your first 2 standards, adding and subtracting. We did a lot of same signs add, keep, common sign, different signs subtract, extend, only goes farther. And we took everything we know about fractions and decimals and applied that to it as well. Standard 3 was all about, what was it all about? Conversions, right? That's where we learned I can take any fraction and convert it to a decimal, and you guys got better at recognizing if it terminates or repeats. And then we also worked on multiplication and division, same signs positive, different signs negative, and we recognized that if we have a mix, if I have fractions and decimals, then I can change them all to the same form and still do all those calculations. So a lot of that stuff in the number system strand was just taking things you'd already learned in elementary and applying some new things to them, but also just getting more efficient at them, getting better at them all. And we're going to continue that now. But this new strand we're working on, and that word strand I keep saying is S-T-R-A-N-D. It's just how your standards are laid out. Number system is the first strand. This is the second strand, and it's E-E, 2 E's. Now, what do those E's stand for? In order to find out, I would like you all to get out page 19 from your math binder. It's called Angelo's birthday boxes, and this particular task is going to help us figure out what is that first E, what do one of those E's stand for. So grab your pens, pencils, whatever you're using, and let's be ready to go. Okay, Angelo's birthday boxes. Right up here it says, each year for his birthday, Angelo receives a birthday box. In the box, he always finds bags that contain dollar bills, plus a few other dollar bills scattered around the box. The pictures below give visual representations of Angelo's birthday boxes for the last 4 years. This is a task that I made it up, but at the same time, it's based on true experiences, because this is what, when I hit an age where my grandma didn't know what to buy for me anymore, she actually did this for me. She'd get a big box and she'd actually put a bunch of shredded confetti paper in there, and then she'd put some dollar bills and some bags of money, and I just had to dig through it and find it. And it was like my favorite thing every year. So my grandma actually did this. But for this pretend scenario, Angelo's birthday boxes have looked like this. This is a visual of what his 9th birthday looked like, 10th birthday box, 11th birthday box, and 12th birthday box. I want you to just focus on part A right now. If Angelo knows that each bag always contains the same amount of $1 bills, do any of the boxes have equivalent amounts of money in them? How do you know? I'm going to read that first part again. If Angelo knows that each bag always contains the same amount of $1 bills. So does Angelo know how much money's in a bag? We do not know how much money's in a bag, but we know whatever it is, it's the same in every bag. Okay, if that is the case, do any of these birthdays have equivalent amounts of money in them? Pay very close attention to this. How do you know? You guys have found out that when you upload pictures of your math binder notes and you haven't quite written as much as I think you should write, that's when you don't get full points. And I say, hey, please make sure you show me how you know, or write everything you see in the video and stuff like that. So make sure you're not just telling me, yeah, these ones are the same, or yes or no, or whatever. If you think some of them are equivalent, tell me which ones and tell me how you know. This is that moment where you're going to pause me and just answer part A. Okay, in order to answer this question, we first had to really make sure we understand what that pink underlined word means. Equivalent means the same mathematical value, or this represents the same amount. So a lot of people recognize pretty quickly that the 10th and 11th birthdays do have equivalent amounts because they have the same number of bags and the same number of bills. And here's one of the really cool things about mathematics and what we're moving forward with is there is definitely an unknown in this scenario. There's a thing we don't know. We don't know how much money's in a bag. In fact, grab a pen right now. We're going to add something to this part A. This, I'm going to scroll my page down a little. You see that? See that in pink there? There is something called an unknown in this scenario. What is the unknown? The thing we don't know? We don't know how much money is in a bag. So I even put a question mark on it because I was like, how much money is in a bag? I don't know. In math, we also sometimes call that the abstract. It's the thing we don't know, okay? But the cool thing is even when you don't know something, you can still work with it. We also, in this scenario, don't know how much money's in a box. But again, that comes back to how much money's in a bag. Because as soon as I know how much money's in a bag, then I can figure out how much money's in a box. So really our key unknown here is how much money is in each bag. Now we do know we have something called a constant. So I'm going to scroll my paper a little bit more and you can see this last part. We have something called a constant. The constant is how many bills are in the box, which we also refer to as a concrete value. Unknown, abstract, how much money is in a bag. Constant, known or concrete value is how many bills are in the box. We can see that very clearly. That's a known constant value. Now, sometimes we think of constant as being the same all the time, and it can mean that. But oftentimes in math class, when we say it's a constant, it just means we know it. We know exactly how much it is. So now let's take a look at part B, okay? Part B says, write expressions. And I have some stuff already written on this one, so I'm going to switch papers so I can write this down with you guys. This part says write expressions to represent each of Angelo's birthday boxes. Well, here you go, you guys. This is that first E, expressions. And this is not brand new to you. This is something you definitely worked with in 6th grade, but we want to bring it back and make sure, again, that not only we remember it, but we actually get better at it. Okay, so one of the things we have to do when we consider an expression is we have to give ourselves some kind of model, some kind of representation for the unknown. And you know what we do with that in math? We make it a variable. I'm going to use the letter B. You can use whatever letter you want, but why might I use the letter B? Well, because my unknown is this. Let's write it again. What I'm going to write here, B represents how much money is in a bag. One of the coolest things we do in mathematics is we represent an unknown with a variable. And as soon as we do that, then we can still work with it. And this is the point in class where I'd say, okay, can you guys write an expression for each of these? And I get all kinds of fun results. So I'm going to show you one thing that I'll often see is take a look at you've got it on your paper. Can't see it on my screen, but look at your paper. Look at the 9th birthday box. Look at the bags that you see and look at the dollar bills that you see. I still don't know how much money is in that box, but I do know I have a bag and another bag and another bag and another bag, and I see $4. That can be an expression that represents this scenario. Look at the 10th birthday. I could say there's a bag, there's a bag, there's a bag, and there's 9 extra dollar bills. Okay, 11th birthday, I see a bag, a bag, a bag, and 9 extra dollar bills. Huh, does this show us another representation that verifies that 10th and 11th birthdays are in fact equivalent? Whereas the 12th birthday, I see a bag and a bag and a bag and 10 extra dollar bills, which tells me these are probably never going to be equivalent no matter what's in the bag. Could these be? I don't know, maybe. Depends on what's in the bag. Now, some people look at that and they go, Miss McGowan, I didn't write it that way and probably wouldn't write it that way. Doesn't it just make sense if I say, okay, there's 4 bags, can't I just write 4 times B? Well, yes, absolutely, because multiplication is just repeated addition. And you know what's even more brilliant? I'm going to show you how to clean it up and be more efficient. You don't even have to write 4 times B. You can just write 4B. And in mathematics, when you put them right next to each other, and this probably looks familiar from 6th grade, but if you put them right next to each other, you can automatically assume multiplication, and then you don't have to write it. Plus 4. Now here's a really important question that I have for you. Should I add those together and call it 8B? No, that wouldn't make any sense, right? Do I have 8 bags? I absolutely do not have 8 bags. I have 4 bags and I have 4 bills. Those are not the same thing. So this is as far as I can go with this representation. I cannot combine bags with bills. I can't do anything more with this until I know how much money's in a bag. Which means this one, I can say 3B, 3 bags, plus 9 bills. And again, I'm not going to put those together because I don't have 12 bags and I don't have 12 bills. I have 3 bags and 9 bills. Keep them separate. Okay. However, this is equivalent to this. They look a little different, but they are in fact equivalent expressions. They are equivalent expressions. They represent the same thing. This one is also 3B plus 9. Another verification that 10th and 11th birthdays are equivalent because they have the equivalent expression. Whereas this one is 3B plus 10. In mathematics, you have unknowns, which we let be variables, and you have constants, which you definitely know. And all of it can be put together to model something with mathematics in an expression. And that is the first E that we're going to be working with for the next couple of weeks here is expressions. And then I'll kind of keep you in suspense and we'll find out later what the other E is. What's the other E? But right now you're going to focus on expressions. And next week we'll do some more with equivalent expressions and seeing how to work with